Hi, in the last lecture we have been deriving Bernoulli's equation and discussed about the limitations of Bernoulli's equation due to the assumptions that were made in the process of the derivation. Okay, so Bernoulli's equation for an incompressible flow can be written in this form, and we have given two different physical viewpoints of this equation. Okay, so one is that it is the conservation of mechanical energy, where you can see that the sum of kinetic energy, potential energy and the flow energy are constant along a streamline during steady flow when compressibility and frictional effects are negligible. Okay, so one viewpoint, these are the things we have already seen in the previous lecture. One physical point of view is that this is mechanical energy conservation. Another way we can state is that the work done by pressure and gravitational forces acting on a fluid particle is used to increase the kinetic energy of the particle. Okay, so these are the things we have discussed in the last lecture itself. So in many mechanical engineering applications, okay, in many applications, not all, but in many applications, potential energy change can be neglected. Potential energy change can be neglected. So for example, if you're applying Bernoulli's equation to gas turbine engines, okay, the change in kinetic energy or the change in kinetic energy or change in the flow work is much higher than the change in potential energy. Okay, so in that case we can neglect the potential energy out of this equation while applying Bernoulli's equation to such systems. Okay, so in such scenario we can remove potential energy, and I'm going to multiply the equation by rho g. So I'm going to get P plus half rho u square is a constant. Okay, so here we have two terms. The first one is what do we call as static pressure. Okay, so this is the equivalent of actual thermodynamic pressure. So when we say pressure in a fluid flow, we always refer to static pressure. Okay, so or simply we call it pressure. So when we say pressure, we always refer to static pressure. Okay, and the second one is called dynamic pressure. It's called dynamic pressure. It's not actually pressure, but this is kinetic energy expressed in the unit of pressure. Okay, so it is not actually pressure, but it's actually kinetic energy possessed by the fluid particle, but we write this in terms in the unit of pressure. Okay, and the constant we call this as P0, and P0 what do we call as stagnation pressure. Okay, so stagnation pressure is nothing but the sum of static pressure and dynamic pressure. So it is defined as, so when we say stagnation pressure, we are saying that so when we so a particle flowing in a fluid has both static and dynamic pressure. Stagnation pressure is obtained when we decelerate the flow isentropically to zero velocity. Okay, and the pressure you obtain will be static pressure. Okay, suppose if you have a pressure measuring device, okay, and you keep it in a fluid flow, it actually pressure static pressure. So if you have a pressure measuring device, okay, it actually measures static pressure or simply pressure. Okay, so at a particular point, at a particular, let's say I am considering a diffuser, flow in a diffuser. Okay, so let us say at this point I am keeping a pressure probe. If I measure using the pressure probe, if I measure pressure, I will get static pressure. Okay, so the flowing fluid has static pressure as well as dynamic pressure associated with the kinetic energy. If we want to measure stagnation pressure, what we do is, theoretically, what we have to do is we need to decelerate this particle to zero velocity. Okay, let us say, so this has reached zero velocity. Let us say this location is 2. Now if you measure the pressure here, you will get stagnation pressure, because all the kinetic energy they expressed in terms of dynamic pressure is converted into static pressure, because you see sum of static and dynamic pressure is a constant. Now when you decelerate the velocity to be 0, dynamic pressure goes to 0, so what you get is stagnation pressure. Okay, so if you decelerate the particle isentropically, then you measure pressure, you will get stagnation pressure. Okay, by isentropic, by now you must have learned in thermodynamics course, by isentropic deceleration means we mention no energy losses. Okay, there is no heat transfer, which is already implicitly assumed in the derivation of Bernoulli's equation. Here in this context, isentropic deceleration, we mean there are no energy losses associated with friction or any other factor. Okay, so you should know stagnation pressure is obtained by decelerating the flow isentropically to zero velocity. Okay, that should be clear. So this viewpoint of so this equation, Bernoulli's equation expressed in this form, is used to measure velocity in a fluid flow using what do we call as pitot static tube. Okay, so in pitot static tube, so what we have, so pitot static tube is used to measure velocity of fluid at a point by measuring its stagnation and static pressure. Okay, so pitot tube will have so pitot tube is placed in a fluid flow facing the direction of the flow. Okay, so the direction is moving from left to right here. So pitot static tube is placed facing the flow, aligned with the direction of the flow. Okay, so there is a point here. Okay, when the flow comes and hit here, the fluid decelerates, and the velocity of the fluid at this point would be 0. Okay, so this measures stagnation pressure. Okay, and then there will be a small hole perpendicular to the direction of the flow, okay, where the flow velocity is not actually 0, but the fluid flows with its own velocity. So this measures static pressure. Okay, so these two, let us say the flow is airflow, for example. These 2 points are connected to 2 ends of the U-tube manometer, which is filled with the manometric fluid of density rho m. So let's say the velocity, the density of the fluid is rho, the density of the manometric fluid is rho m, and we will have the height different to be hm. Okay, so this leg has stagnation pressure and this has static pressure. Okay, so the one that has stagnation pressure will have what to say, the depth, the meniscus will be on a higher side in terms of static pressure than stagnation pressure, because P0, the stagnation pressure is larger than static pressure. Okay, so now as you know, the manometer, U-tube manometer is used to measure pressure difference. So P0 minus static pressure P, okay, is rho m g h m. Okay, this is directly from the U-tube manometer equations that we have discussed. So we measure difference between stagnation and static pressure using pitot static tube, which is given here as rho mghm from the manometer reading. Okay, from Bernoulli's equation we know that, so Bernoulli's equation says that P plus half rho u square is P0. Okay, so from Bernoulli's equation, P0 minus P is half rho u square. Okay, so this is the density of the flowing fluid, this is density of the manometric liquid. Okay, so from the above equations we can write half rho u square is rho m ghm. From here you can write the velocity of the fluid is 2 hm by rho. Okay, so this is how we measure velocity of a fluid flow using pitot static tube. Okay, here one point we need to mention is that theoretically stagnation pressure means isentropic deceleration, but in practice isentropic deceleration is not possible. Okay, so this is not an isentropic deceleration. We are bringing the fluid to a sudden halt. This is not an isentropic deceleration, so there will be some error in the computation due to this fact. Okay, the deceleration is not isentropic. Okay, in practice isentropic deceleration is not possible. Okay, as a result there is an error in the computation due to this fact. Okay, so the discussion of the error is beyond the scope of this course, but now what you need to know is how Bernoulli's equation is used in pitot static tube, which is used to measure the velocity of a flowing fluid. Okay, so is it slow? Okay, what is going on? Yeah. Okay, great. So this is an actual picture of pitot static tube. You can see the hole here. Okay, this is the hole used to measure stagnation pressure, and there are holes. So this leg of the pitot static tube is aligned in the fluid flow in the direction of the flow, facing the flow direction. You can see here. Okay, the flow is happening from left to right here. So this particular leg is aligned along the direction of the flow, and this hole faces the direction of fluid. So velocity will come and attain a zero velocity here. Okay, so these perpendicular direction, these holes in the perpendicular direction measures static pressure. Okay, which are here. Okay, so this is the actual picture of pitot static tube. Okay, so there is something called, this is not directly relevant to Bernoulli's equation, but there is something called pitot tubes that are used to measure only stagnation pressure. So the objective of pitot tubes not pitot static tube, but pitot tube is to measure stagnation pressure that is heavily used in airplanes. You can see here. Okay, this is a pitot static tube, and this is how it looks. Okay, this flow, the airflow will come and hit zero velocity here, so there will be some form of pressure measuring devices attached to it, which is used to measure stagnation pressure in airplanes. Okay, so let's stop here. Thanks.